Thanks to the organizers for this opportunity. And so I'll be talking about syntactic multilinear branching programs. And this model is in connection with what Srikanth introduced in the open problem session yesterday. The results in this talk are a joint work with B.V. Raghavendra Rao from IIT Madras. So we all know what multilinear polynomials are. If you look at the degree of any variable in a monomial, it's at most 1. For instance, determinant is a multilinear polynomial. And syntactic multilinear branching programs are natural models to compute multilinear polynomials. For instance, if you look at this is an algebraic branching program where if you look at any S to T path, every variable appears at most once. So if you look at this blue path, every variable appears at most once, whereas if you look at the red path, x1 appears twice. So if you now flip one of these x1s to x2s, the resulting branching program is syntactic multilinear. One of these x1s to x2 or x3, then along any S to T path, every variable appears at most once. So such branching programs are called syntactic multilinear branching programs, and syntactic multilinear branching programs naturally compute multilinear polynomials because along any path, a variable appears at most once. So we'll call this SMABPs for short because it's difficult to say this every day. So size of this branching program is the number of nodes in it, and width is the maximum number of nodes in any layer. That's the parameters we look at. So the best known lower bounds, size lower bounds for syntactic multilinear branching programs are almost quadratic in the number of variables. So this is a result due to Alon and others. So it's n square up to a log square factor. So this is barely quadratic in the number of variables. And there's an explicit n variate polynomial. So the goal of this talk is to understand how to prove super-polynomial lower bounds for syntactic multilinear branching programs. What are the approaches and what are the challenges? So a slightly different model for computing multilinear polynomials are multilinear formulas. So this is what Srikanth was talking about yesterday. So arithmetic formulas are circuits where if you look at the graph, the underlying graph is a tree. And multilinear formulas are formulas where every gate computes a multilinear polynomial. So the entire formula computes a multilinear polynomial. So in the case of multilinear formulas, we know a super-polynomial lower bound on the number of variables due to RAS. So RAS shows that any multilinear formula computing the determinant or permanent polynomial must have size n to the omega log n. So we want to understand how to prove lower bounds for branching programs. The best known lower bounds are quadratic here, and the best known lower bounds are super-polynomial here. So a natural approach would be to convert this branching program into an equivalent multilinear formula and use the techniques to prove lower bounds for multilinear formulas to get lower bounds for syntactic multilinear branching programs. So this is a very folklore result. If you look at any syntactic multilinear branching program that computes an n-variate polynomial of size n to the order 1, you can convert it into a multilinear formula computing the same polynomial with a super-polynomial Biopan size. So if you start with n to the order 1, the resulting formula will have size n to the order log n. So now this results in two approaches to prove lower bounds. The first is, suppose you were able to improve this conversion. That is, if you start with an n to the order 1 size branching program and you convert it into a multilinear formula of size n to the little o of log n. If you are able to do this, then RAS lower bound for multilinear formulas is sufficient to get a lower bound for branching programs, right? So that's one approach. Another approach is to improve the lower bound for multilinear formulas. If you can get n to the little omega of log n lower bound for multilinear formulas, then this conversion is itself sufficient to give you a lower bound for syntactic multilinear branching programs. So these are two approaches, but both these approaches seem difficult at the moment. With the techniques we have in hand, this seems unapproachable. So for the rest of the talk, I will require one preliminary, which is the partial derivative matrix. So given any polynomial f on 2m variables, y1 to ym and z1 to zm, the partial derivative matrix of f is the following matrix. Rows of the matrix are indexed by multilinear monomials in y, and the columns are indexed by multilinear monomials in z. So this is, you have 2 to the m many monomials in y and 2 to the m many monomials in z. So this is a 2 to the m cross 2 to the m matrix. And the pqth entry of this matrix is the coefficient of the multilinear monomial PQ in F. That's the partial derivative matrix. And the partial derivative matrix satisfies both these properties. It's sub-additive and sub-multiplicative. So now suppose you are given a polynomial f on n variables x1 to xn. You can look at partitions of the variables into y's and z's. You have n by 2 y variables, n by 2 z variables. Consider two partitions, phi and phi prime. So the first, so here it's not assumed to be variable disjoint. So here I have not assumed variable disjoint. If they are, then this will be equality. Oh yeah, here it is not. So if f and g are variable disjoint, then this is equal to, and only in that case fg will be multilinear. So now we will consider two partitions. The first is x1 going to y1, x2 going to z1, and so on. So if you look at the rank of each of these are rank 2 matrices. So the rank of the polynomial mf with respect to the partition phi is 2 to the n by 2. I mean, each of them would contribute 2. Whereas there's another partition where x1 goes to y1, x2 goes to y2, and so on, such that the rank of this polynomial under the partition phi prime is 1. So if you look at a polynomial under different partitions, it can get different ranks. That's the point. So when both y and z have cardinality exactly equal to n by 2, the rank is at most 2 to the n by 2, because here m is n by 2. So these are some basic preliminaries. Okay. So we know that with the techniques currently in hand, it's unapproachable to prove syntactic multilinear lower bounds for syntactic multilinear branching programs. So what exactly is this talk about? If you look at a multilinear formula and you want to prove strong lower multilinear formula, it seems to be difficult because you have to show n to the little omega of log n. But if you start with a syntactic multilinear ABP and convert it into a multilinear formula, probably the formula has more structure than an arbitrary multilinear formula because it's coming from a syntactic multilinear branching program. So somewhere you need to use that. So this talk we will look at a finer analysis of the techniques that RAS used to prove lower bounds for multilinear formulas. So in short, this is what we'll do. We want to upper bound the rank of the partial derivative matrix of a polynomial that's computed by a syntactic multilinear branching program. This seems difficult at the moment, so I'll convert it into a multilinear formula and then upper bound the rank of that. So we also know that there are polynomials that have full rank. So what I mean by full rank is, look at any partition phi of the variable set. We know polynomials g such that if you look at the rank of the matrix mg phi, it's 2 to the n by 2. That is, for any partition, it achieves rank 2 to the n by 2, full rank. So such polynomials are called full rank polynomials. So in case this did not make sense, it would make sense eventually. Okay. So you start with a multilinear formula. We'll do an analysis of multilinear formula and then see how to convert the branching program into a multilinear formula. So for consider a multilinear formula here phi, and there is a gate v. So we'll do fv, the polynomial computed at gate v, and xv to be the set of variables that are in the formula rooted at v that appear here. These are xv's. And if you look at any to VL, you know xv1 in xv2 is contained in xv3 and so on. So for any v1 to VL in the formula, we'll denote by signature of phi the sequence xv1, xv2, so on up to xvl. It's the sequence of variables that appear along the path. And I need some definition, so I'll just introduce this. You say a signature is central. If you look at the growth of the variables along the path, it's not too much. That is, at every stage, xvi plus 1 is at most 2 times the cardinality of xvi. And this is true for every vi on the path. Such signatures are called central signatures. So the question is, why are we interested in signatures of this form, where the growth is not too much? If you look at this definition of central signatures, it's not even clear if there should be one central signature in the formula. But by induction, you can actually show that in any formula, there is at least one central signature that reaches the root. So there is one, there could be more. In fact, every signature could also be central. We do not know. So far, we have seen signatures and what central signatures are. If you consider a partition phi from x that takes the x variables to y variables and z variables, and you have this multilinear formula, there are gates v1, v2 and so on. If you apply phi to this variable set xvi, it would either be y variables or z variables like this. Some of them would be y, some of them would go to z. Right? You say a central signature, so these orange signatures are all central in this picture. You say a central signature is k unbalanced if there is some gate in this path such that if you look at the variables of that gate after you apply the partition, either the number of y's is k more than the number of z's, or the number of z's is k more than the number of y's. So such signature, you say a signature is k unbalanced with respect to a partition phi if it satisfies this property. So with respect to one partition, a central signature could be k unbalanced, whereas with respect to some other partition, it need not be. So why are we interested in k unbalanced central signatures? If you consider this polynomial f and consider two partitions, the first one takes all the variables to y. So there are 4 y variables and no z variables. The imbalance is 4. Like the difference between the number of y's and the number of z's is 4. And the rank of this polynomial is 1. Because all of them go to y, only the first column would be filled in that matrix. Whereas if you consider the second partition, the imbalance is 0. That is exactly 2 y variables are there and 2 z variables, so the rank is 4. It's a full rank. So this in some sense says that if you have higher imbalance, then the rank is low. So I'll need one more definition, this is the last. So you say a formula is k weak with respect to a partition if every signature that is central is k unbalanced with respect to this partition. So here are some orange signatures, and if all of them have a node where their imbalance occurs, then you call this formula k weak. So why are k weak formulas interesting? You know that if a central signature is k unbalanced, then the rank is sort of low. So if every central signature is k unbalanced, then the rank of the resulting multilinear formula needs to be low. That's the intuition. So if phi is k weak, then if you look at the polynomial computed by that multilinear formula with respect to this partition, it should be low. So 2 to the n by 2 is the maximum rank, and if the formula is k weak, then the rank is k by 2 far from being full. But there is a multiplicative factor of size of the formula, but it's not full, it's far from being full, it's low rank. So we will be interested in k weak formulas in particular. So with all these definitions, I think we can start with an approach to show lower bounds for syntactic multilinear APs. The first is start with the syntactic multilinear branching program of size s and you convert it into a multilinear formula. So if you start with size s, you will incur a blow up in size, which is s to the order log n, and the depth will be order log n of the resulting multilinear formula. So let us assume for the moment that s actually computes a full rank polynomial. P is the ABP, right? So when I mean full rank polynomial, under any partition it has rank 2 to the n by 2. So consider a distribution where the partitions are all balanced. You know that if phi is k weak, then the rank is low. I convinced you that if phi is k weak, it has to be that rank is low. So when is it that this property is not satisfied, or what are bad formulas? So if you pick a phi at random from this distribution, by definition, this formula is not k weak if there is a central signature that's not k unbalanced, because k weak means every central signature is k unbalanced, right? So if it's not k weak, then there is one central signature that's not k unbalanced. So by union bound, this is the number of central signatures times the probability that a central signature is not k unbalanced. Now let's look at the red part first. You know that every central signature is a sequence of variables and it has length log n because the depth of the formula was log n. So V1, V2 to VL, L is log n. So using hypergeometric distribution, if you set the value of k to be n to the 1 by 5, you can show that this probability is very low. It's like n to the minus omega log. So the log n comes from the fact that central signatures have length, it's a sequence of variables of length log n. Now suppose you are able to show that whenever the size of the branching program is small, n to the little of 1, the number of central signatures is n to the little of log n. Suppose you are able to show this, then this probability is less than 1. Because this is n to the little of log n and this is n to the minus omega log n. So then with probability less than 1 or little of 1, the formula is not k weak. Right? Which means with probability 1 minus little of 1, it's k weak. In other words, the rank is, so when you substitute k equal to n to the 1/5 here and size of the formula to be s to the order log n, you will get that the rank is strictly less than 2 to the n by 2 with high probability. But that is a contradiction because you assumed that this branching program was computing a full rank polynomial. So the only assumption that you made here was s is n to the little of 1. Suppose I was able to show this. Let's assume that the blue part is done. Whenever the size is small, the number of central signatures is small. If you can show this, then the only place you assumed was that size is n to the little of 1, which should be that. So it should be a contradiction and s should be n to the omega. Yeah, so that would also be fine, but I just wrote it for n to the little of 1. This could be n to the order 1 and you can put little omega of 1 because I said super polynomial. So if this is clear, then if there are any questions, I'll probably take, because this is the approach used for the rest of the talk. So what we need to show is that if you start with small branching programs, the number of central signatures is small. This seems to be a roadmap to prove super polynomial lower bounds, but there is a roadblock. So even for read-once algebraic branching programs, it could be that the number of central signatures is large. And why would it be that whenever the size is small, the number of central signatures is small? So it could be that the number of central signatures is n to the omega log n. So we look at read-once algebraic branching programs and try to clear this block. There is, okay, so I'll do this slowly. So you have a read-once algebraic branching program on the left. So a read-once algebraic branching program is every variable appears in one layer, and if you look at all the edges in this layer, they will be labeled only by single variable. So we'll assume x1 to xn to be the order in which the variables appear. And there's one notation that I'll need. So uv is the polynomial computed in the subprogram with source u and sink v, this branching program. So I do the following. I look at the layer after which n by 2 variables are read, and then write f as sum over all I equal to 1 to w sui times uit. So the polynomial f can be expressed like this. So this naturally gives a formula. So there's a sum gate whose fan-in is w, and then there are two product gates. There are several product gates. Every product gate has fan-in 2. This computes su1, u1t, and so on. So if you look at the variables, the potential variables at every gate, so the root gate could potentially compute a polynomial in x1 to xn because it computes f. And if you look at each of these product gates, it computes su1 times u1t. So these are also potentially polynomials in x1 to xn. And each of these children are polynomials in n by 2 variables, like x1 to xn by 2, xn by 2 plus 1 to xn. The way we divided it, this is how it should be. It could potentially be, but some of the edges can contain constants, so the variables can be missed. But if at all, then this will be the number of variables. And this formula, if you look at it, every time we'll go down on the number of variables by 2. So this will have depth order log n and size s to the order log n. The formula obtained from an ROABP. So now since this is obtained from an ROABP, each of these gates you can associate it with intervals from the original branching program. So SV be the interval associated with gate V. So one thing to note is the actual set of variables could be a subset of this because some of the edges will be labeled by constants. So XVs are actually subsets of SVs. But the observation is the following. If you look at any sum gate that has children V1, V2 to VW, and if you look at the intervals associated with this, all of them would be the same. Because that's the way you did the division, divide and conquer, like SU1 times U1t, SU2 times U2t and so on. So all of them would be the same set of variables. And at a product gate, like this, the set of variables SV will be 2 times the set of variables of its children, the size of its children. So this is something you can observe from this. Now this is not exact, so when we looked at signatures, for V1 to VL, we said the signature is XV1, XV2, so on up to XVL. But this is not exactly the signature, if you look at the SVIs, but it's an extension of the signature, because the sets XV are contained in SV. So we'll define extended signatures for a path row to be the sequence SV1, SV2, so on up to SVL. So it's an extended signature sequence. So why is this useful? So similar to the central signature property, you can also define these extended signatures to be central. Right? You say an extended signature is central if the growth of the variables is not by much. But from the previous observation, you can see that if V is a sum gate, then the cardinality of SV is exactly equal to the cardinality of the intervals associated with children. If it's a product gate, it's twice. So if you look at any path, this property is going to be satisfied. Either SVI plus 1 is SVI if it's a sum gate, or it's 2 times SVI if it's a product gate. This means that every extended signature in the formula is central. So this is one example where every signature was central. So here is the formula. You have a path V1 to VL, and the associated extended signatures are SV1, SV2, so on up to SVL. So why is this useful? So if you count the number of extended signatures, at a sum gate, you see here, at a sum gate, the sets are going to be the same. At a product gate, you incur 2 sets. So, and the depth of this formula is log n. So the total number of such signatures is 2 to the order log n, which is like order n. So you wanted to show that if you start with a branching program of small size, the number of central signatures is small, but it seemed like for RABPs it can be n to the omega log n. But the number of extended signatures is still small, it's order n. But this crucially used the fact that this multilinear formula came from an RABP. Otherwise this interval property would not be there. So using this, so if you look at the template that we had, that was the only block that we had, and now you can replace it with order n. So in that case, you can actually show a lower bound for some of RABPs. That is, if you have F1 to Fm, which are polynomials computed by read-once branching programs of size S1 to Sm, and if there is a polynomial that is computed by a sum of read-once branching programs, either the number of sum n's need to be large, which is super-polynomial, or there is one RABP in this summation that has large size. So this you can do by converting each of these RABPs into a multilinear formula and then proceeding with the roadmap that we have. Since the number of extended signatures is order n, you'll be able to show this, but I won't get into a proof of this. So this is just to demonstrate that signatures, the sequence of variables along a formula that is obtained from a branching program are relevant. But for this model, you actually know exponential lower bounds. I'm just writing it here for superpole. So now, so this was for RABPs. This was for RABPs. Now what do we do in the general case when you consider a syntactic multilinear ABP where this read-once property is not there? So there could potentially be many central signatures, right? It can be n to the omega log n. But it could be that there are these nice central signatures. If they are unbalanced, then the other central signatures are roughly unbalanced. Like if each of these central signatures these nice central signatures in green are k unbalanced, then the ones in orange, the ones that are not good, are almost unbalanced, like k minus delta unbalanced. So even if you had this property, it would be sufficient. You actually wanted a set of central signatures that whenever they are unbalanced, the rank is low. But it could be that this is not the case. But there could be a small set that's a pivot. Like if each of these are unbalanced, then everybody else in the set is roughly unbalanced. So in other words, what we want is we want a small set of central signatures that in some sense cover all central signatures. Like these small sets are unbalanced and everything else needs to be unbalanced. So one candidate for this is the following. You look at a set of central signatures in this formula that is obtained from a branching program, and you put, for every signature, you either put this signature in the pivot, I mean the nice set of central signatures, or you put another one that meets this as a multiplication gate. So why is this useful? Because if the green ones are the nice ones, they are all like k unbalanced. If you look at the orange ones, they will meet this green paths at some multiplication gate. So whenever there is a loss in rank here, since this is a multilinear formula and at the multiplication gate the children are variable disjoint, this rank would sort of percolate up. Once you have a loss in rank, this rank will percolate up. So it's enough to actually get a small signature cover. Yeah, so I'll just come to it. So what exactly is delta we need to see, and how do you ensure that this is true? So if you look at a signature cover, it looks like this is true, though I'm not giving a proof. Because if this, so the signature cover is the green signatures, and the ones outside it are the orange signatures. So if the green ones are k unbalanced, then the orange signatures are like, since it meets it at a multiplication gate, this would also be unbalanced. That's the intuition. So if there exists a signature cover such that every central signature in this cover is k unbalanced, then the rank is 1. So this is something that we can show. So then so you started with signatures, then you came to central signatures, but it looked like central signatures are a plenty. So now it's enough to actually come up with a signature cover where every central signature is k unbalanced. And this is sufficient to do the job. So answering what he said. So let's start with the signature cover. So you know that if every central signature in this cover is k unbalanced, then the rank is low. That's something I just assumed you believed on this statement. So now what he was asking was, how do you define this delta, right? So you have these signatures that are k unbalanced. I want everybody else to be like k minus delta unbalanced whenever these are k unbalanced. So there should be a measure of closeness between these signatures, such that whenever these are k unbalanced, the remaining of them are like k minus delta unbalanced. And the natural notion of closeness is the symmetric difference. So you look at two signatures, which is xi1, xi2, so on up to xil. So ci and cj are two signatures, and these are the variable sequences. And you look at the distance between them. So when I say distance, it's the symmetric difference, or the difference in the sets of variables. And you look at the maximum among all of these, and define that to be your capital delta. Now, so if these two are like delta far, how different can the number of variables be between xi1 and xj1? There can be like at most 2 delta variables that are different. Like anyway, the symmetric difference is delta. So if you can come up with, so we started with signatures and got to signature covers. If you can come up with this nice cluster such that if you look at the signatures in this cluster, every signature is, so for every signature that's outside the cluster, there is one in the cluster to which it's delta close. Then you'll be able to get that whenever these nice green ones are unbalanced, the orange ones will also be at least k minus 2 delta unbalanced, because the difference in the number of variables is only like, the difference is only 2 delta. Like the symmetric difference is delta, so there can be only 2 delta variables that are different at every point. So the observation is, if all the central signatures in the delta cluster are k unbalanced, then every signature is at least k minus 2 delta unbalanced. That's what we said. because the symmetric difference is delta, at most delta. So the summary of all this is that it's actually enough to find a signature cover with a small delta cluster. You actually wanted to come up with small number of central signatures. You weren't able to do that. That's possibly not doable. So now it's actually enough to come up with a small delta cluster. So the entire approach can be summarized as follows. If you start with a syntactic multilinear branching program of size S, and if you can convert it into a multilinear formula of size S to the order log, and this you can do. But if you can do this with the property that there is a delta cluster of a signature cover with at most S to the little o of log n signatures, then you will be able to apply that roadmap to get a contradiction that S needs to be n to the omega 1. But I want delta to be like less than n to the 1 by 5 for the hypergeometric distribution to work. So it could be that there is a cleverer distribution for which this can be much larger. It's just that for the roadmap that I wrote, we had applied hypergeometric distribution. So in essence, this would imply a super-polynomial lower bound, that is n to the omega 1 lower bound, capital omega of 1 lower bound, for syntactic multilinear branching. So one challenge in doing this is that, why should this property be true? There could be multilinear formulas of size S where if you look at any delta cluster, it has like large number of signatures. But one of these statements need to be true. If this is true, then you have a lower bound. If this is true, then these are in some sense the hard multilinear formulas that you need to look at. So possibly these are the candidate ones. So that's the end of the first approach. So the next approach is via ordered branching programs. So if you look at a syntactic multilinear ABP, sorry.
That is a polynomial which is not full rank, but it's
full rank under R partitions. Yeah.
The definition of central signature has nothing to do with what the.
No. So the definition of central signatures here is actually inspired from. So in RAS, if you look at it, if you look at any multilinear formula of size S, it can have at most S central paths. But the paths are actually not important because several paths can have the same signature.
No, but the fact that that particular polynomial does not have polysize formula. So does that say that you could in principle have S to the omega log n central signature? If you take that polynomial and just convert it to a polynomial.
What is the number of central signatures in the resulting formula?
Maybe you take it off.
Yeah. Okay. So maybe that's a witness to the fact that.
Yeah. Maybe.
Yeah, it could be that this challenge is actually true. So if you look at a syntactic multilinear branching program, if in any S to T path, a variable appears at most once. So you can view the variables on S to T paths as permutations in Sn. Right? So if you look at read once algebraic branching programs, every path reads variables in the same order, which means that there is one order that governs the entire branching program. Now as a natural extension to it, you can consider a bag that contains L permutations, and if you look at any S to T path, it should read variables in one of these L orders. So these are called L-ordered branching programs or bounded order branching programs. So I'll first describe this result. So we have a lower bound for sum of L-ordered ABPs. So we fix L to be 2 to the n to the half minus epsilon. Then there is this polynomial G such that if you write it as sum of L-ordered ABPs, then either M should be exponential or there is an ordered ABP in this whose size is large. So it's like a dichotomy. It can't be that this polynomial is computed by a small number of small ordered ABPs. So now the question is, how many orders can a poly in n size branching program have if it's multilinear? So anyway, there are only 2 to the n multilinear monomials. So any poly in n size ABP, if it's computing a multilinear polynomial, it can be at most 2 to the n orders. But can we say that if you start with a poly in n size SMABP, it has at most 2 to the little o of n orders. Can we say that? If we could say that, then this would also imply a lower bound for syntactic multilinear branching. But even that's not necessary. That's not just one approach. Another way is you can start with a syntactic multilinear ABP of size poly in n, and if you can express it as a sum of sub-exponentially many sub-exponentially ordered ABPs, then this result would give you a lower bound for syntactic multilinear ABPs. So that's why looking at how many orders poly in n size ABP can admit if it's multilinear. So those are like two approaches. The other one is via low depth formulas. So we all know that if you start with a branching program of size n to the order 1, then it can be depth reduced to a depth 4 multilinear formula. This is due to Tavenas, Agarwal, Vinay, and this also holds for, this also preserves multilinearity and it also holds for circuits, but I have written it here for branching programs. If you look at this depth 4 formula and the polynomials computed by the bottom sum gate, so you know that it's like a sum of products where the fan-in is order root n. So these polynomials are degree order root n, the bottom sum gates, but they could potentially be on n variables. Can we reduce the number of variables? Like, can we say that the arity of these bottom sum gates is order root n? So this is what we show. If you start with a syntactic multilinear branching program of size n to the order 1 that computes an n-variate polynomial, you can depth reduce it to a depth 4 multilinear formula, which is the sum of products of order root n polynomials, each on order root n variables. The number of variables is not large, but there is a considerable blow up in size. So with this, you would get another approach that if you show 2 to the little omega of root n log square and lower bound for these kinds of formulas, depth 4, then you will get n to the little omega of 1 lower bound for branching programs. So the best known lower bound for these kinds of formulas is 2 to the omega root n. So you need to improve this exponent to get a lower bound. And there was this recent result for multilinear circuits, which is similar in spirit due to Mrinal and Ramprasad and Raphael, that actually starts with a multilinear circuit, syntactic multilinear circuit, and does VSBR based on the number of variables to get a similar depth 4 multilinear form, where the lower sum gates have bounded arity. So that's actually pretty much it. So this is a summary of what the talk was about.